they let you do this really hard thing of reliably distributing a bunch of work and make it much simpler. And the way what this means is that when you can write a workflow that enqueues a bunch of tasks and then waits for those tasks to complete. And then maybe enqueues a bunch more tasks and waits for them to complete, or does some processing on the results of those subtasks. And those subtasks can themselves be workflows that can enqueue more workflows. So you can create this really complex program that distributes a lot of work, waits for someone to complete, distributes some more work. That work can itself be complex. And all of this is a workflow or a nested tree of workflows and child workflows. And that means it's all reliable. The progress of every one of your workflows is checkpointed so that if your big complex program fails at any point, it can automatically recover from where it left off. And that means you can write these really complex distributed programs that distribute a lot of work and worry a lot less about failures, about how to make them fault tolerant, and about what happens if you just enqueued 5,000 jobs, but you also have to enqueue 5,000 more and suddenly your server crashes. All of that complexity is being handled for you. So how do these queues actually work? At the core, DBOS enqueues workflows, queues durable workflows. Every queued item has to be a durable workflow. So then the DBOS queue is really just the main DBOS workflow status table. When you enqueue a workflow, it's written to the status table with a queue name and a status of enqueued. And then all of your servers can pull that table to define new work on that queue and process that work. So the main pull query kind of looks like this. There's a lot more to the polling query than this, mostly to do with flow control. There's like a lot of additional work in this query that figures out what concurrency limits there are, what rate limits there are, and respects them. But at the core of the query, at the core, each of your workers is regularly polling each of its queues for new work, new and queued workflows, and selecting it and then taking those workflows and executing them. One really important part about this query is that this query is optimized using Postgres locking clauses. So workers don't just all try to get the same new workflows because that would cause a lot of contention in Postgres and be really slow. Instead, each worker queries for new work using a locking clause so that it atomically finds some work and locks it. It atomically finds the first piece of unlocked work and locks it so that other workers won't try to take the same work. And what this means is that these Postgres-backed queues can be really efficient. Many of our users are scaling to thousands of concurrent servers or workers, all trying to read from the same Postgres-backed queues. And because the queues are designed with skip locked to minimize contention, all these workers can read from the same queues with no real issue. The database can handle this level of concurrency. So now I want to talk a bit more about what you can do with queues. So first I want to talk about this core set of flow control primitives that queues provide. And then I want to talk a bit about how those primitives can be composed together into some more advanced queue patterns you can use to build sophisticated distributed programs. And the cool thing about each of these primitives I want to talk about is that they're composable. So we have these different concurrency limits and rate limits and all these can be put together. So like building blocks. So you can apply whatever types of limits or restriction, design whatever concurrency limitations you want in your queue. Make it do exactly what you need. So the most basic flow control primitive that queues provide is worker concurrency. You can control how many workflows from a single queue can run on a single one of your processes, a single one of your workers or servers. And that's really useful when your workers, like for example, your workflows are resource intensive. So if you run too many workflows on one server, you'll run that server out of memory. So you can set a worker concurrency limit to make sure that no server runs too many workflows concurrently and your servers never run out of resources. Then what you could also do is set a global concurrency limit that controls how many workflows from one queue can run concurrently across all of your processes. And it's actually a bit of a much riskier thing because if you set a global concurrency limit, then any kind of slowdown or disruption on any of your processes can actually impede the queue across all your processes. So this is there because you sometimes need it. Uh, Sometimes you need to, you're dealing with an API that really has global restrictions. But just be aware this is a risky thing to put in your program because it means that any one of your workers can block all of your other workers. Of course, you could pair this with a worker concurrency limit to make that safer. Then another similar flow control limitation are rate limits. So you can control how many workflows can start on a queue in a given period of time. You can say that this queue can only launch 50 workflows per minute globally across all your workers. And maybe that's useful if you're dealing with a rate limited API, like a lot of these LLM APIs that we're building with these days. You also, if you're applying a ton of limits and concurrency limitations, you might want to use priority. You might want to say, well, most of these workflows will only run one at a time, but sometimes I've got a really important workflow that should jump to the head of the list and should be the first workflow run no matter how many other people are waiting in the queue. And then you can do this with priority. You can say that some of my workflows are special. Maybe they're for our favorite customers. And those will always run first before any other workflow. Or we can have multiple levels of priority, even if you have long queues with many limitations. Then there's one more of these flow control building blocks, and that's explicit queue listening. By default, every one of your servers will read and dequeue workflows from every one of your queues. But sometimes your servers are different. Some of them servers might have GPUs, some servers might have CPUs, some servers might have more memory. And you only want certain servers to process certain tasks. You only want the tasks that require a GPU and your data pipeline to go to the servers that have GPUs. So you can uh, set certain servers to only explicitly listen to specific queues. And that way you can have one application with one system database and one namespace that spans a bunch of heterogeneous servers where each server is only doing a particular type of work. But any server can enqueue anything to any queue, but each server will only read from and dequeue and execute work from a specific queues. Okay, so those are the core building blocks of queues. I want to pause for a minute to see if anybody has any questions or things we want to discuss, and I'll go a bit more into how you can compose those together into some more advanced queue patterns that let you build really powerful applications.
Yeah, Peter, we got one great question from Mahit. Mahit, it's great to see you, man. And as always, like you've made great contributions to DBOS, and this is a perfect question, I think, to discuss. The question is, because we are polling for unqueued jobs, does that affect our latency from unqueue to DQ?
Yeah,
And what are the expectations there?
yeah. So fundamentally, the latency, the latency from enqueue to dequeue is going to be determined by the polling interval. The polling interval is configurable. So if you need higher latency, if you need very low latency, you can set a low polling interval. But of course, that comes as a trade-off because then you're doing more read queries against the database. For ultra latency sensitive tasks, I'd probably recommend against using queues. I'd probably recommend against distributing those in general. If they're really latency sensitive, try to execute them from on the place where they arrive from. Uh, but that depends on the particular use case.
Perfect. Perfect. Another one just came in from Michael. I'll read the question first. If a workflow fails, how long before a workflow row is released? And can any worker pick up the failed job, or will it have to be the same one that failed it before? I think there may be a bit of confusion in the question between erroring out and recovery. And maybe we can go through both of those
Yeah, so a
cases.
few different things here. So the lock is actually held for a very short period of time. The lock is only held in between when a worker selects a workflow for dequeuing and when it actually dequeues the workflow by changing its status from in queue to pending. And then once the status has been changed to pending, the workflow is the lock is released. And now the workflow is a pending workflow and it's owned by that worker. So
Hmm.
then let's say that the worker fails. The worker crashes or something and it doesn't proceed and it's no longer executing the job. The it's no longer executing the workflow. So then let's assume you're using Conductor. So one thing Conductor does is it detects these failed workers. It sees that one of your workers has failed, it's no longer executing its workflows. And it then instructs another worker to recover those workflows. And what that worker does is it takes all those workflows and the ones that were originally in queued, it actually puts them back on the queue. So it takes that workflow and it changes its status back to in queued and it puts it back on the queue. And then this half completed workflow can then be picked, it's back on the queue now, and it can be picked up by any worker that's reading from the queue. But it has to actually be, it has to go through the queue. It has to get back to the front of the queue again. And that way, even during recovery, the reason we do it that way is so that even during recovery, uh, queue flow control limits are respected. So this is actually really important. Let's say you have a worker concurrency limit of 3 because your workflows are really memory intensive, and then half your servers fail, and the other half have to pick up all the work. Well, you don't just want one server to pick up all these memory hungry tasks. That's going to knock over the server. So instead, one server gets the recovery requests. It puts all those tasks back on the queue. And then your remaining servers will slowly dequeue and recover and finish these workflows. But they'll do it in fully respect of all flow control limits because those workflows went back on the queue so that your workflows all recover, but without ever violating your limit, your flow control.
All right. I think that's all the questions we got for now. Let's keep going into the advanced stuff, huh?
Okay. Yeah. So here's like some of the cool things you can do by combining or composing some of these flow control primitives. So maybe the simplest one is in order processing. Let's say that you're receiving events from some endpoint or a webhook, and you want to process them sequentially in exactly the order in which they arrive. So you can do that via a queue with a concurrency limit of 1. So you set up this queue with concurrency 1, and then you can have each of your you can have your endpoint just directly enqueue the workflow and then return. And then no matter how many events you're getting, no matter how long it takes for them to process, no matter no matter how many events you're getting, no matter how long it takes for them to process, each of them is going to be put in the queue in the order in which they arrived. Each of them will be dequeued and process that order, and you can get, in a distributed setting, sequential in order processing of your events. Another pattern that's a bit more complex, but also really valuable, is partition queues. So sometimes you want to apply flow control limits, not globally, but per customer or per tenant or per ID or per something that shows up dynamically. Like maybe you're running a multi-tenant system with many different customers, and you want to apply flow control limits per customer. You want to say that each customer can only say do one task at a time. You want a per customer concurrency limit of 1. So to apply, these sorts of limits, to something dynamic like customers, you can use partition queues. So you define a partition queue, and then whenever you enqueue a workflow into a partition queue, you have to do it with a partition key. And then all flow control limits on the queue, its concurrency limits, work concurrency limits, rate limits, whatever, those are all applied per partition and not globally across the queue. So you create a partition queue, set a concurrency limit of one, and then enqueue each workflow with the tenant ID as the partition key. And now you are processing tenant tasks with with a concurrency limit of one per tenant. And then what's nice about this is that this is fully dynamic. As new tenants come in, you can just use those new tenants as IDs as new partition keys, and keep creating new partitions on the queue and apply all of your limitations per partition. The way this works under the hood is that DBOS essentially treats each of these partitions as a virtual subqueue, and it's pulling and applying limitations to each of these subqueues separately. And that's a bit optimized so that only the active partitions are being pulled, so that you can have huge numbers of partitions with actually fairly minimal polling. So this allows you to efficiently do essentially dynamic queue generation across partitions. Then the other thing you might want to do is you might want to have both global and per partition limits. You might want to have a fair queue where you have globally limited queue capacity that's fairly divided across multiple tenants. And you can do that by combining regular queues and partition queues. You define a partition queue with your per partition limits, and maybe that's a limit of one workflow per tenant. Then you define a global queue with your global limits. Maybe that's a worker concurrency of 5 globally. So you want to make sure that each of your tenants, only one item can be processed at a time per tenant, but also no worker ever processes more than 5 items at once across all tenants. And that way no tenant can flood you, but also no tenant can overwhelm your capacity by submitting 10,000 tasks at once because only one will be processed at a time. But also no worker can be overwhelmed by tasks from too many tenants because each worker has this working concurrency of 5. So you define these two queues, and then what you do is you enqueue a workflow first to the partition queue and then to the global queue. And that way, both sets of flow control limits are applied to the workflow, and your workflow then respects both the per partition and the global limits, and you could do fair queuing with whatever sorts of flow control limits you want, both across tenants and globally. Another thing you might want to do is, this is going in a slightly different direction, but I want to jump around between some of the cool features that the DBOS queues support, is debouncing. So sometimes, especially in more reactive applications, you don't want to process inputs immediately. For example, let's say that somebody's editing is editing a text box. You maybe don't want to process every single keystroke they make on that text box. You only want to process the result when they actually when they stop editing and they're ready to submit. So what a debouncer does is it delays enqueuing a workflow until some amount of time has passed since a user has stopped submitting inputs, and then it processes the last input submitted. And that way, you can, for example, build, let's say that you want to validate an input that a user provides to a form. You can wait until maybe a few seconds have passed and since the user has stopped updating the form, and then submit the workflow that does input validation. And that way, the user sees whether their input is valid or not, but you also don't run a million of these workflows for every single one of your users' keystrokes. So this is a way to integrate workflows into a more reactive or human scale latency application without totally overwhelming your system. Then one last feature I want to talk about, not so much a queue pattern, but a new feature that I just want everybody to know about, is that through Conductor, DBOS now supports alerting for queues. So you can create alerting rules either for when your queued workflows fail or for when your workflows are stuck. When workflows are on a queue for too long, and that might indicate either a failures in the workers that are processing those workers or some sort of issue that's slowing the workers down and it's caught or a system being overwhelmed, so you've built up a backlog on your queues. So you can set up alerting rules for either the failed workflow or the slow queue case in Conductor. And then if those conditions arise, it will trigger a handler that you can set up in your program in your DBOS application that you can then use to say uh, fire a Slack alert or alert PagerDuty or what have you. So, if your queues are critical in production, well, you can now set up automatic alerting for them, so that if something goes wrong with your queues, if they fail or if they get stuck, you'll know. Okay. One last thing I want to touch on is what's coming next. A couple big improvements we want to build for queues. More concurrency primitives, particularly a dboss.waitFirst, that lets you enqueue a bunch of things and then wait for one of those to complete, so you can process enqueued events. You can enqueue a bunch of things and then process the results as they come in instead of waiting for them all to complete. Some new scheduling primitives, like saying, I want to enqueue this, but not now, but tomorrow. So it'll go on the queue tomorrow. Better syntax for fair queuing to make it easier to do multi-level queuing, and also better support for bulk operations like bulk and queues. So you can perform big operations across many queues. It should be easier to enqueue, say, 10,000 things at once. Okay, so that's it for queues. Let's talk about let's kind of discuss this a bit more, then we can go on to the roadmap.